Here we go. Okay, so we looked at the collision of the line with the plane this morning. Okay, so now we're going to look at the collision of a line with the sphere. So typically, this might be used where you've got a projectile that's been fired. We're going to consider it moving in a straight line, and you have a spherical bounding volume, which might be a close approximation volume for a roughly spherical object, the torso of the gorilla or the head of the person or something, or it may be an outer bounding volume, an outer bounding sphere. So you just want to detect, is there a chance that the projectile might hit an object that's inside the sphere? If you do detect a collision of the projectile with the sphere, then there's a chance it might hit some more complicated object within the sphere, and then you could carry out a more detailed collision detection analysis to see if it might hit something more complicated inside the sphere. And if it misses the sphere, then you don't need to go and carry out that complicated collision detection. Okay, so this is the setup. So I just quickly outlined this last time. That diagram illustrates all the known data about the problem. We've got a fixed sphere. We're dealing with a stationary sphere here. It's fixed at a particular point. And we locate it by locating the center of the sphere. So the position vector C at the center of the sphere is known. The size of the sphere, the radius of the sphere will be known. And the starting point P of the projectile will be known. And its velocity vector will be known as well. Yeah. So that's kind of the setup. That's all the ingredients. So those will be known values in any particular simulation. And that's a typical intersection. Well, what's illustrated there is the projectile intersecting the sphere in two distinct points, okay? An entry point and an exit point. But there are, of course, other possibilities which we'll end up classifying or describing. Okay. So just the end of this paragraph here is, figure 3.3 illustrates one scenario, but of course there are others, and our task now is to give a precise description of them all. Okay. So what's the vector equation of a sphere? How do you describe the sphere with vectors? Well, there we've located the center and we've specified its radius. But to describe the surface of the sphere, to describe the spherical shape, well, that's described by this vector equation here. So we'll let the vector x be a point on the surface of the sphere. And what characterizes x as being on the surface sphere is if its distance from the center is the radius of the sphere. Okay. And what's the distance of the point x from the center point C? In vector terms, it's simply the magnitude of the vector x minus c. Okay. So x minus c is the vector which points from the center out to x. And if that has magnitude r, that means x is located on the sphere. Okay, so x is on the sphere if and only if this equation here is true. Magnitude of x minus c is r. Or another way of describing that, to bring in a more standard vector operation, is to think of that in terms of the dot product. Remember, the dot product is the square of the magnitude. So if we will think of the equation of the sphere as this second one, that the dot product of x minus c itself is equal to the square of the radius. So those two equations are equivalent. Yeah, they're equivalent. So we'll kind of pick up the second one and run with that. Okay, we'll also use x to denote. Using x, it looks like to denote two different things, but ultimately we're going to be looking at where they intersect, so where x satisfies both conditions. So that's kind of like hey, normally we try to use different variables for different things. So using x to denote a point on the projectile trajectory as well, well, we're considering the thing as a bullet or something moving in a straight line. So there, the possibilities for x are p plus td. Think of the time in this analysis, the time starting at 0, p is the initial point of the projectile where it's fired from, and v is its velocity vector. So p plus tv, we'll keep seeing that again and again. That's the position vector on a linear trajectory. Okay, so we're doing the intersection. It's quite standard approach. We've got these two descriptions of the two vector shapes, the line and the sphere. We want to see where they intersect, so we just impose both descriptions. Both descriptions must simultaneously hold for a point x. Okay, so this gives us the intersection or collision condition. X intersects sphere. X is the point of intersection of the line and the sphere, if and only if this equation here now. So we take the equation of the sphere, the x minus c, dot product equals r squared. We take the vector equation of the line, x is p equals tv, and we simply mush them together, collide them together if you like. So we replace the x with p plus tv. Okay. So this equation here now is the equation representing the intersection, if there is one, of the line and the sphere. Now, okay, it's a load of vectors, dot product equals r squared. Look at it and think, what's known to us, what's unknown to us? Well, everything in that equation is known to us except the time value t. We're looking to see if there exists a time such that that equation holds true. The p, the b, the c, and the r are all known to us in the setup of the problem. So this is a single equation in the unknown t, so we would hope to be able to solve it, and we can. Now, at the moment, t is buried inside the dot product. If you want to get at t, you're going to have to break apart the dot product or carry it out. So expand the bracket. Okay. So, well, I don't go through each boring step by step, but when you expand the dot product and tidy it up, you're left with this equation here. But you can see what happened, and you're left with this expression here, and I've tidied it up with the view to looking at t. So expand out this and tidy it up with your concentration on t. And you see, the thing is going to be a quadratic in t, because you'll have some bits where you have a vector tv dot product with a vector tv, so that will create t squared. You have other bits where you've got a vector tv dot product with other vectors which don't have a t in them. So that will give you something multiplying t, scalar dot product value multiplying t. And then you've got other vectors which are independent of t, just fixed vectors, dot product, other vectors. They'll create scalars in the quadratic equation. Okay? You just expand it all out. Keep careful account of signs, because there's some minus signs in here. And we can express the thing like this. So we've got, maybe I shouldn't have brought back in the norm notation. Maybe I should have left it as, I kind of avoided the norm notation at the top, but now I've brought it back in. So you could consider that quadratic really as v dot v t squared, and then plus the rest of it, 2v dot v minus c t plus, well, you see, the advantage of the norm notation is it's kind of slightly narrower on the page, shorter on the page, if you like, especially when you got these combinations, minus r squared. So that's the equivalent thing, but just using all dot products everywhere. So yeah, so the norm allows us to shorten some of the descriptions. But when you're immersed in vectors and doing this all the time, norm squared and dot product of a vector with itself should just kind of meld in your mind. And, they're interchangeable. They're synonymous. So like, when you see norm squared of something, you think in your mind, well, that's the something dot product with itself. When you look at one, you can instantly interpret it as the other one. Okay, well, that's a quadratic equation in t. Okay, something we're very well familiar with. So we could call that an alpha t squared plus a beta t plus a gamma equals 0. where the coefficients alpha, beta, and gamma are what they are. Norm v squared for alpha, 2v dot p minus c for beta, and this combination for gamma. Norm of p minus c squared minus r squared. R is the radius of the sphere, remember? Well, we all know how to solve a quadratic. We don't need to dwell on that. We use the quadratic formula. And if there is a solution, the quadratic formula tells you what it is. Of course, there may not be a solution. There may be no time at which the line intersects the sphere. That would be the case when the quadratic formula has no solution. And maybe some other ones, which we'll describe now. But the first thing to look at when you're thinking about which solutions there are, which solutions exist, is to look at the discriminant of the quadratic. That's the square root of beta squared minus 4 alpha gamma here. So we kind of defocus on the detail of alpha, beta, and gamma and just focus on the discriminant as something we can calculate. Of course, the alpha, beta, and gamma, it's all known stuff. It's all data from the setup of the problem. Well, if the discriminant is negative, what does that tell you? That tells you that the thing misses completely. Okay? So there's no real solutions t. There's no values of time, positive or negative, for which the trajectory could intersect the sphere. Okay? So we should add in little sketches of these. There's a little sketch you can do for each. There's the trajectory, and here's the sphere. It's just a complete miss. So that's a negative discriminant. The discriminant may be 0. What does that mean? If the discriminant is 0 in the quadratic formula, that means, in general, we think of if there are solutions, there's 2 distinct solutions. But when the discriminant is 0, it means it's just a single repeated root of the quadratic. Okay? So that would be where you've got the sphere and a single point of intersection. I haven't drawn the line in yet. This is maybe 2 possible iterations here. If the discriminant is 0, we've got a single t, but it still could be positive or negative. And if 0 discriminant and a positive value of t, that would suggest this kind of scenario, where it's a single solution, and that's where the linear trajectory just kisses the sphere, just a single point of intersection. Touches the sphere at one point. If t is negative, though, the situation was this. The thing was fired in that direction, but if you continue the trajectory backwards in time, there'll be a single point of intersection. But typically, in terms of the simulation of this environment, that wouldn't count as an intersection. That wouldn't count as a collision because it's a collision in the past, which never occurred anyway, because the projectile only started its life here at this point, at this beginning point here, and moved on. Okay? So we recognize that when we've got a single solution t greater than 0, that's this. Of course, that's just intersecting at a single point, so that's like a glancing blow, if you like. Pull a prism past your head and just scrape a bit of skin off. We're very lucky. Now, whether you treat that as an actual collision in the environment or whether you ignore it and say the bullet missed, well, that's up to the finer points of how you're designing the environment and what kind of level of realism you want to represent. If the sphere is an outer bounding volume in this case, so it's just representing the space within which there is a far more complicated object, then you'd probably ignore this case and say there's no possibility for a collision. The complicated object is somewhere inside the sphere. So, that's still not really a proper collision in the typical sense of the word. Any questions on those 2 points? Or is that all right interpretation of that? Okay, well, if those cases don't happen, that means we've got a strictly positive discriminant.
We've got two real solutions of the quadratic. That's kind of typical situation you think of where you've got solutions to your quadratic. And just to discuss them, I mean, there's still multiple cases of what can happen. So we'll think of T1 being the smaller solution and T1 being the larger solution. T1 is less than T2. Now, one situation is that they could both be negative. The two values of times, the two values of time you get are negative. Well, that's this kind of situation where the thing is shot away from the sphere, but if you hypothetically could continue to project it backwards in time, yeah, you'd have 2 points of intersection. So this is this case here, T1 less than T2, less than 0. Another situation to pick apart is if T1 is negative but T2 is positive. Well, that is the situation where somehow the projectile began life inside the sphere. Shot out this way, so you have 1 point of intersection here in positive time, and you have 1 point of intersection there in negative time. The projectile was actually shot from inside the sphere. Now, perhaps that might point to some fault or bug in the environment if what is supposed to have been the situation was something being fired from outside the object. But maybe, maybe that might be a scenario. Maybe you're looking just to, you are shooting something from within a spherical bounding volume, and you're trying to find the point where that exits the boundaries. So that may or may not be a correct scenario in the environment. It depends on what's going on in the environment. Otherwise, so if none of these cases hold, then what we have is we've got two strictly positive solutions, T1 and T2. There's 2 points in the future at which the line intersects the sphere. The earlier one is when the line enters the sphere. The later one is when the line exits the sphere. So that's this situation here, which is the one illustrated in the original diagram, where you've got the line, the linear trajectory starting outside the sphere, and it intersects the sphere twice. But typically, the simulation of the environment would still be comparing these time values, T1 and T2, to the bound delta T. Remember, we're quite a simplifying assumption, but we're thinking of the system. The system is at some moment in its evolution, and it's simulating what the environment is going to look like in the next frame of the animation. It's just stepping forward in a tiny amount of time. And if these intersection points are happening later than the time of the next frame, because after the bound delta t, then the collision isn't going to occur before the next frame. So you can just move everything on its appropriate amount in the movement of the object, render the frame, and the collision is going to happen sometime in the future. Or if T1 is less than the bound, this last bullet point here, then yeah, the collision is going to occur by the time the next frame should be shown. And the animation says so. There is a genuine collision. We'll need to take explosion, break apart the object or something, some appropriate action, some kind of physical simulation will need to take place because you've got a genuine collision. Yeah, question. What would that mean? Somebody? Yeah, so the three values might come from a cubic. Yeah, so you would have to have a cubic. Yeah. There is indeed. It looks more, it's not as nice as the quadratic formula. Nobody can remember it. Can you remember it? No? I can. All I know is there is one. I can't remember what it is. But I mean, dig a bit deeper into your question. Could you get three t values out? I mean, if you just step back to the original setup, you're talking about a line and a sphere, straight line. And it's just to do with the basic geometry that either you have one point of intersection where you just kind of kiss the sphere, or you've no points where you completely miss the sphere, or you have 2 points where you enter the sphere and then exit the sphere. Well, that could only, I mean, okay, what could be going on that would produce 3 points? Well, really it might, be something like this, or, where you've got a non-linear trajectory, which might enter and exit the sphere multiple times. Then you might have many future values of t. But if it's a straight line and a sphere, well, if it's a straight line and a sphere and you end up with a cubic, that's a sign that there's something wrong in mathematics. That's kind of my answer. If it's a line and a sphere, there can only be no points of intersection, 1 point or 2 points. There can't be 3 points, not in Euclidean geometry. Maybe in other types of strange geometry, straight lines, whatever that means in those geometries might intersect spheres multiple times. Let's think about that a little bit. Having hyperbolic geometry and geometry, other kinds of things. But are you satisfied that, like, with a straight line, it's either 0, 1, or 2? Yeah. Any other questions? That's a good question. No, it's a good mathematical question. It's good instincts there. Like, you see a situation, okay, Killian's just described no solutions, 1 solution, 2 solutions, and then he stopped. Why didn't you continue? Why didn't you look at 3 solutions, 4 solutions? That's a good natural question to ask, testing the boundaries of the thing. Have I given a full account? But with this setup, it is either 0, 1, or 2. Any other questions at all? Okay, I mean, there's a little numerical value, or numerical example here, example 3.1, where you're given a particular sphere, center, particular radius, and particular trajectory, and asked to analyze it and find out if there's any intersections. Should we have a look at that now, maybe? I think I'll leave you to work through that yourself. I mean, it's just following the output. It's just launching into this thing. So this is our known vector C there. That's our radius R. This is the position vector, the initial position vector P at the thing, and this is your V. It's just feeding it all in, working with the algebra. Maybe I'll leave you to. While we're acquainted with the problem and acquainted with the vector setup, I thought we'd go on to this more, okay, at first glance, far more complicated setup. What if the sphere itself is moved? Okay, so in the game, let's say you're shooting at a moving object. Okay? The object you're shooting at is moving. Maybe you're not shooting with a bullet, maybe you're shooting with something like a bow and arrow, something which travels much slower. So you don't aim directly at the object. Maybe you try and anticipate the motion of the object and aim somewhere where it's going to be at the time the arrow gets there. That kind of hard shooting problem. So the system has to look at the movement of the projectile and the movement of the sphere and test whether a collision occurs there. Okay, so that looks more complicated because now both things are moving. Before, the sphere was stationary. But as long as we're thinking of things moving with constant velocity, which they may not be, but as a first approximation, the movement of a bullet, movement of something else whizzing through the scene, can very often be just treated as straight line, constant velocity movements. Well, in that case, really, the analysis is essentially the same once we make a certain move. Okay? If we have a fixed origin and two moving objects, the sphere and the line, then yeah, there's, everything's moving and the situation is you have to take account of that. However, why leave the origin or why leave the frame of reference fixed if everything is moving? Why not attach the frame of reference to one of the moving objects? Because at least then you can treat that object as being fixed. If the frame of reference moves with one of the objects in the scene, then at least you've got one fixed object then. And if everything is just moving with constant velocity, it's easy to adjust the velocities to make them all relative to your new moving origin. Okay? So that's the principle. And once you do that, then you're back to the original. If we attach the origin to the moving sphere, then the sphere is stationary. And we're just back to this simple setup, which we've already solved. So let's just look at how that's done. So we use the same setup as before, except now the center point C of the sphere is no longer stationary. It itself is moving, and we're going to think of that moving along a linear path. So that's C is actually a function of t. C is a function of t. C is q plus tw. Ignore that cylinder. That's the figure for the next problem. So C is q plus tw. The bottom of the previous page is the top. So now the collision is going to occur when the position x of the particle is within the distance r of the center point, and you just, proceed as before, and you have this dot product equal the radius squared equation. It's looking more complicated because we've now got the starting and moving information for C. But you just kind of take a deep breath. It's still just t is the only unknown thing here. So you just take a deep breath, expand out the quadratic, and organize it in terms of t, and you get this quadratic equation here. Now before, we just had the magnitude squared of the velocity of the projectile as the coefficient of t squared. Now we've got this new coefficient, which is the square of the magnitude of v minus w. The v minus w has a natural interpretation. V minus w is the velocity vector of the projectile after the origin, the frame of reference, has been attached to the moving sphere. Okay, so it's the relative velocity of the projectile relative to the sphere. V minus w. And you see v minus w again occurring in the coefficient of t. And it's multiplied, that product is being taken with p minus q. And what's p minus q? P minus q is the relative position, starting point of the projectile relative to the starting point. So everything is just made relative. Magnitude of p minus q squared is a constant term in the quadratic. Again, that's the relative position vector, starting point of the projectile relative to the starting point. So it's a quadratic. It looks more complicated, but it has the same structure as the previous one, and it's just interpreted as being relative velocities and relative position vectors relative to one of the moving parts, relative to the moving sphere. So again, you've got a quadratic alpha t squared plus beta t plus gamma. You've got adjusted values for alpha, beta, and gamma, but the analysis then is essentially the same. So it's the same sequence of bullet points, exactly the same treatment here of the discriminant in this problem, and it's the same interpretations that hold. It's essentially, once you make this step of considering relative velocities, relative position vectors, the problem reduces to the previous or simple problem of the stations. Okay. Any questions about that? Or? Okay. Okay, so the second half of chapter 3 is about capsules. The capsules. The thing about spheres is spheres do a good jobs for roughly spherical objects, but you know, not everything is roughly spherical. So we have this idea of the human form being approximated by torso and its limbs and maybe the head. Okay, the head is a sphere, but then it's more realistic to use what I call these capsules for the torso and limbs. Okay? So capsule, remember, is a cylinder, but not with flat ends, but with hemispherical, half spherical ends. Okay? Look like a big medicine pill, those medicine capsules. Okay? So using bunches of capsules, you can produce bounding surfaces, collections of bounding objects for your more complicated objects that are in the virtual environment. So again, we want to look at the intersection problems. Okay? And the ones that we're going to treat here are the intersection of a line and a cylinder. Yeah. So when you're looking at whether a line intersects the capsule, it's kind of hard to write down a single vector description of the capsule because it has a kind of cylindrical middle part to it, but then it's got two spherical ends. You can't kind of write down a single short vector equation for the whole object. So we split the capsule up, think of it as the cylinder, separate from the two spherical ends. So the first intersection problem we tackle is a line and a cylinder. Whether the line intersects the cylinder part of the capsule. And then once we have the solution of that worked out, we can then bring in the hemispherical ends, which remember are just spheres and inserted into the ends of the cylinder, and test for intersection of the spherical ends. Okay. So, but as you can see, I mean, you just look at it on the page, the analysis is slightly more lengthy. Okay, there's more stuff to look at. Okay? So that's what we're going to do on Monday. So I don't want to rush through it now, because there's a few subtleties to consider in it. Then we're going to do the line and the capsule, and finally we're going to look at things. We've looked at linear trajectories, which typical case we think of as the trajectory of a bullet. But another type of collision we'll want to be able to handle is when typically some object, whether it crashes into a wall. So there you're looking at, does something intersect the plane of the plane? The plane representing the side of the building, or the floor, or the ceiling. The intersection problems we're going to look at there are if and when a sphere intersects a plane. And the other one then is if and when the capsule intersects a plane. Now you can see quite clearly that I don't have much to say about whether a capsule intersects a plane. That's because the problem reduces essentially to looking at whether a sphere intersects a plane. Okay, so on Monday, we'll dive into the guts of whether the line intersects the cylinder. Maybe we'll just end by returning to our little example here. Where was it? the line intersecting the sphere. This example 3.1 here, maybe we can have a go at solving that. So I wonder, do I have MATLAB here? Do I have MATLAB here? Okay. Do I? No. No. Yes. Starting MATLAB. There's the example. So let's look at how we just do look at the solution in MATLAB. John was showing me before I had a zoom text. The problem is that text is tiny. It had some weird way of zooming it. There should just be a zoom button here, but we went and said, see, that's the thing. Why should we go in settings? So this is why MATLAB isn't good. I shouldn't do this. Font. I'm sure there's a shorter way. They have to have thought of a shorter way to do it. Okay, that's better. I mean, maybe I'm teaching you how to suck eggs, as they say, but so let's just type in the initial data. So we've got C, center point of the sphere, which is 310. I'm showing you this because I want to encourage you to get used to verifying your answers. So you've got a position vector C, you've got the radius R, and you've got the initial value of the bullet, which is 0, 2, 0. And the velocity vector of the bullet is 1 minus half. That's all our data, isn't it? So I'll jump straight away. You can talk about that. Top. Let's just straight away work out what alpha, beta, and gamma are. Okay. There's our stuff at the bottom. So what's alpha, beta, and gamma? Alpha was the norm of b squared, wasn't it? Norm of b squared. And use that formula for that. Beta is 2 star dot product of b with p minus c. Good, we get a beta. And gamma was the norm of p minus c squared minus r squared. Good, so my alpha, beta, and gamma. So what did the alpha, beta, and gamma? The alpha, beta, and gamma give us the quadratic. So we set up the quadratic expression. Oh, and I'm going to start talking about t now. MATLAB doesn't know what t is. See, everything I've typed in has been numerical values so far, or combinations of existing values. But I'm going to start mentioning a t, and I haven't defined t yet. So you need to tell it that t, for the moment, is just going to be treated as a symbolic variable. So now I can use t in the definition of stuff, even though it doesn't have an exact value. So what's the quadratic? Well, it's alpha t squared. That's beta star t gamma. You don't always use whole words for variable names, but sometimes nice. It makes the code easily understandable. So let's just solve it. are there values of t for which the line intersects the sphere? Solve command. Oh, look, solve, and I need to tell it the equation and maybe tell it the variable. Probably not. And you can probably guess what the variable is because there's only one symbolic thing in it. Let's see how clever it is. Let's just type in the equation. Now, of course, the first time you type in the equation, you type in that. That's wrong. Why is that wrong? What does MATLAB try and do when it sees that? Quadratic equals 0 is an instruction to set the value, assign the value 0 to quadratic. It looks like an equation, but it's not. The equation, setting up a statement, setting up a logical statement, something that might be true or false, versus you use the double equals sign. So solve the quadratic equals 0. Answer 2. Good. That seems to work. I was thinking maybe I had to do that. I'll probably give me the same answer. Yeah. I didn't need to tell it to solve it, but see, because it looked at the equation and it saw there's only one symbolic value. So we get two values, 2 and 22 over 5, 2 and 11 and 2 and 4.5. No, 2 and 4.4. Thank you. 2 and 4.4. So after 2 seconds and 4.4 seconds, the line intersects the sphere. So 2 seconds is the earlier one. So 2 seconds after time 0, the line enters the sphere, and at 4.4 seconds, it exits. So if this thing is a bullet, then experience would be bullet. It's 2 seconds to go across it. But maybe it's a slower kind of object, and smaller sphere. Now, no, the sphere is ready 2, but you have to wonder what the units are. Okay? So I mean, okay, so it's a pretty, it's nothing too hectic mathematically, but at least it's good practice to check your working with MATLAB. Yes, question. Sorry, doesn't matter. Okay, so maybe I'll